All right, we're recording now. But now that, is it green? Is it purple? What color is it, Isabel? Blue. So the blue segment, where does it come from over on the left?
To the left, like 0, 0, 1.
So since it's in the zero, since the blue segment is in the 0, 1 squares, it will come from the 0, 1 segments. So let's put those 0, 1 segments in blue. And then the other part is in a way deleted. It is not part of where the mapping is going to come from. So let's delete in red if you have a red that works, which is seldom the case. Otherwise, you could just hatch it out or something. Yeah, okay, good. So that is deleted. So we have deleted half of what we started with at the first stage. We are beginning to build a Cantor set on the left. And the first thing we have done is delete the middle, not the middle at all, the right-hand half. So we didn't delete a middle here, we deleted the right-hand side. Does this make sense? Okay, Emma, you want to continue? So this is inductive, like the Cantor set very important material is, or CRUD. And so each, now at the second stage, each of the 0, 1, 2, 3 squares are divided into 4 pieces. So we're over on the squares again. Yep. And now within each partition element, we label again, and it has a specific ordering. That's the 0th one down there. And that is not the first one. The first one is over to the right. Yep. So that's 1. And then 2, and then 3. And then the first square, yeah. And the reason you ordered that way, Emma, is if you would have gone your way, then you wouldn't have ended up at the first big square. You would have ended up at the third big square. Yeah. But you don't want to. You want to keep the ordering the same.
Okay.
I mean, yeah. So, and actually the square that you labeled 0 is really labeled 0, 0, where the first 0 represents the big square that Abby drew, and the second 0 represents the fact that it is the 0th square of the 0th square. So the one that you labeled 1 should be 0, 1, then 0, 2, and then 0, 3.
That makes sense. So then
You with me?
1, 0.
1, 0, yes.
Oh wait, no, this would be, yeah, okay. 1, 0, this would be 1, 1.
It is, yeah, good seeing. Let's label them all.
Oh yeah.
Yes, exactly. And now okay, Abby, you're up then. This is just nerve-wracking. So now we're interested in that the left-hand edge. What's it in at the second stage? Yeah, so it's in. So of the in the 0th square, what part is, let's take that 0 line segment and divide it into 4 pieces.
0, 0, 0, 3, right?
What was that, Abby?
It's 0, 0, and 0, 3, right?
Yeah, 0, yeah, 0, 0, and isn't it 0, 0, and 0, 3?
Yeah, 0, 3.
Yeah. So now what is deleted, or what we're not interested in, is 0, 1, and 0, 2. So now we are deleting the middle half. What we're interested in is in the outside sections.
Okay.
Are you with me?
Yeah.
And now what about in a part of that line segment, that's just the bottom of it. The top of it is in the number 1 square, and it's in the
It's in 1, 0, and 1, 1.
1, 0, and 1, 1. Yeah. So though that's what we want to keep, and the rest gets X'd out with Isabel's big X.
No.
Things get small quickly. Now, so now what we have, at least for these first 2 iterations of the inductive definition, is that because we're looking at the y-axis segment and want to know what maps to that, when we look back and see what maps to it, you can see that nothing from the right-hand side of the unit interval maps to it. And then nothing from the middle of that first interval maps to it. And nothing from the last part of the second interval maps to it. And so let's break down how much we've sort of deleted or is not important to us. First of all, the measure of that Isabel's X is how much, the first one? What was that?
1/2.
1/2, yeah. So 1/2 we've deleted. Let's measure what we've deleted. 1/2 plus, and how much will we deleted at the next stage?
1/4.
Yeah, right. Because we've deleted half of what's left, a total of half. And then what does it look like? How much are we going to delete at the next stage?
An 8.
Yeah, how'd you get an 1/8, Isabel?
Because we're deleting half of the quarter that's left, I think.
Yeah, I see. So yeah, there was a quarter left, and probably we're going to delete half of that, 2 intervals for each of the intervals that we kept. And let's put some plus ... dots, Abby. And then an equal sign. And then what's the answer? Ah, yes. So if we delete a total measure of 1/2, then whatever remains, and there will be stuff that remains, whatever remains will have measure 0, because everything that we're talking about now is in the unit interval, 0 to 1. Does this make sense? Everybody with me here? Okay, so we're going to do a little bit more today, but one of the first things I wanted you to see is this process. When we're looking at vertical lines, for example, in the range, and we want to know what maps to them, you figure that out on a step-by-step basis. And that step-by-step basis will begin to form a Cantor set over in the domain. Now, when you went like this, you know, if it really means this, you should say so, because I need to know when it's like this. I mean, a prof always wants to see this, but what I need to see is this. Does any of this make sense? No. Okay. Yeah. Okay. So this is the main idea. Let's just at sort of random draw another line, a vertical line segment somewhere in your square. Not the left-hand edge, but somewhere else in the square. Put a relatively, not one of the lines you drew, but some other line, just randomly. Okay. So let's array. Isabel, you want to go back to secretarial work? So on the left-hand side, let's erase the unit interval and let's start over.
So a new interval?
Yeah, new unit interval, maybe a little bigger because things get tiny in a hurry here. Okay, and we want to divide it into 4 because that's the way it's divided into 4, into 4, into 4. So base 4 is the way actually to discuss these things, the best kind of notation. But in this case, I can't actually see Abby's, but which of these 4 intervals is used at the first stage? Which are not involved and which are involved?
Oh, on the line?
Yeah, for the line that Abby drew.
So, this one is used, right, 2 and 3, sorry, and 3.
Yeah, that's what I get too. Everybody get that? Because it goes through those 2 squares that are labeled 2 and 3. Okay, and at the next stage, which each of those intervals now will be divided into 4. And at the next stage in the number 2 interval, which are not used and which are used.
So 0 and 1, and then 1 and 2.
And from the number 3, which are used?
1 and 2.
1 and 2, okay. So again, it's sort of the same. We delete a middle part and then keep half of the other one. And what about the measure computation? The measure of what we're removing?
It's gonna be the same as the last one.
Yeah,
0 again.
everybody with this? So I'd like you to understand this pretty well. Let's erase the unit interval again, Isabel. And let's erase the computation. There we go. And Emma, you want to take over? Let's say we wanted a Cantor set of some positive measure rather than 0. So what do you want your Cantor set to measure? Give me a measure, any measure.
A quarter.
I didn't hear it.
1/4.
1/4. Okay, so let's write, how much are we going to delete then?
3/4.
Yeah, so let's write equal 3/4. And can you give me a series then that converges to 3/4?
You do like the 1/2, 1/4, 1/8, but multiply all by 3/4.
Oh,
It's
yeah.
like 3/8.
This is like 1/2 to the n.
It'll be 3 over 2 to 4.
Three over two to the n plus one, I think so. Oh, n plus one. Yeah,
So I can't see, it's 3/8 plus,
so we did basically the series we had before, but all multiplied by 3/4. So 3/4 times 1/2 to the n, ending with 3/2 to the n plus 2.
I see, yeah, yeah. This, you can always do that. There are plenty of series that converge to 3/4, but the easiest one is as half, half again, half again, half again, half again. So that always will work for you, that geometric series. So 3/8 plus 3/16 plus 3/32 plus blah, blah, blah equals 3/4. And those numbers, do you have a plus dot, dot, dot? I didn't see that.
I didn't write it out, so let me do that quick.
Yeah. Yeah, good, good, good.
Sweet.
And so now these represent what we're going to delete.
Mhm.
Are you with me?
From the interval 0 to 1.
On the interval, yeah, so let's put back that interval 0 to 1. And let's use Abby's line as a target this time. So it's going to hit the second and third intervals. So the first two intervals, don't make them even yet. Don't make them even, because you want to delete the first two intervals and get a total of 3/8. So the 0th and first intervals together get smaller. They're only 3/8 long now, so each one is half of that.
Okay.
So approximately 3/8, mark it, and then divide that into 2. And label those 0 and 1. And now divide the next half into 2 and label those 2 and 3. Okay, so far, what is not going to map to Abby's line, what we can eliminate right at the get-go, is the first two intervals, which have a total length of, or total measure of 3/8. Am I right? If you X those out, yep. So they are no longer under consideration. The points that map to Abby's line lie in the last part. Are you with me?
Yeah.
What do we do next?
Now we divide. We would want to eliminate 3/16.
Yeah, so we're gonna, how much do we want to delete total out of those?
And 3/16.
3/16, yep. And how many intervals are we going to remove to do that?
2?
What was that, Abby? Did
Is
you?
it like 2 from, is it, we take out 2 from 2 and then 2 from 3?
I think in your, if you look on the right-hand side, you can see what it is. I think you are, out of the first interval, you are going to keep 0 and 1 and eliminate 2 and 3. Am I right?
Yeah.
So you use 2 and you eliminate 2.
Yeah.
The 2 that you eliminate should have, would be the last 2, and their total length will be let's see, we want a total of 3/16 split between those two, so 3/32 for each. But then there are two intervals for each one, so 3/64.
Oh,
So the next two intervals that you're going to delete are on the interval marked 2, and they're two little teeny ones on the end, each of 3/, what did I say, 64? And the intervals you're going to keep, and there'll be two of them. So you split. So those two are on the right, and then the interval between that, there should be a midpoint there.
yeah.
And then those two you're going to keep.
Okay.
So what we are doing here, or what this process is doing when we're trying to create a positive measure Cantor set on the left, it's always dividing into 4 intervals like the Hilbert way, the standard way, but they're no longer of equal length. Because if you make them of equal length, then automatically the Cantor set that you will get will have measure 0. Because what you're deleting will be half plus a fourth plus an eighth plus blah, blah, blah. You will always be deleting 2 intervals out of each 4 that you create. And so in order that you delete a smaller amount, those intervals have to be smaller. And how much smaller is governed by that series that you have that converges to 3/4. There's a lot of machinery going on right here, but the basic machinery is always, you're going to have on the right-hand side, there's no change. You take the square, you divide into 4 subsquares, you order in a certain way. You label 0 through 3 according to that order. And that describes what maps to what. On the left-hand side, the domain, those are intervals. And if they're always taken to be equal length, then you'll be dividing into 4, into 4, into 4, into 4. You'll always be considering 2, then 2 of those and 2 of those. And so the measure that you will get for the Cantor set will be 0. In order that it's not 0, you control that by changing the lengths of the intervals that are deleted. Isabel, is it like this or is it like this, or are we okay? So I think you need to work through this arithmetic, not the ultimate arithmetic, but you need to see how this goes a little bit. So you'll need to practice with this, because what I would like is, and a good goal for next week would be to see if you can do this in a way so that a positive measure Cantor set maps to the y = 0 line segment, the left-hand line segment. Ooh. Are we okay? We could have used Abby's line, but let's start with maybe a standard line at first as a target. And then later we'll get more complicated targets. But I'd like to do that first target first, so that we see if we can get a positive measure Cantor set to map to that. That means defining a new function. Not the Hilbert function will not do it because it divides evenly. But dividing unevenly in the way that Emma's showing on the board now can do that. And we'll eventually want to divide unevenly so that we can get whatever measure we want between 0 and 1. Are we okay with this part? There's something else I wanted to do today. It's about the same kind of stuff, but let's erase everything and go back to the regular Hilbert function so that we see what maps to what. What is this mapping that is represented by that arrow?
You want me to erase this? And
That one we can keep if you want.
Yeah.
Got Abby fine, but we can ignore that. Abby, you want to go back up?
Sure.
So I'm going to give you an X value in the domain, and I want to know where it maps to. Okay, so I'm going to give you the X value base 4 because that is the easiest way to figure this out. So X is equal to 0.0233. Let me make it easier for a minute here. Let's erase the 233. Let's do 0.011111 repeating in ones. You can put a bar over the one if you want to indicate repeating in ones. And that's X equals that. And then find f of X for me.
So f of x is the output in here.
Yeah, where is it going to be in that? It's going to be in that square. Where in that square is it going to be? Can you narrow it down a little bit?
Here, okay.
It'll be in the 0th, mark the square off, like shade it in for me or something, Abby. So
1501.
yeah, that is the 0, 1 square. Am I right?
Yeah.
Yeah, so it will be in that square. That's correct. But where will it be? I mean, can you narrow it down further?
In like the bottom right corner.
I don't, let's draw a blow up of that 0, 1 square for me. Just the 0, 1 square, yeah. Okay, 0, 0, 0, 1. Oh, so there's the 0, 1 square. So let's think of beginning at one vertex and going to the other. For in the beginning square, the one that has your line and segment in it, mark 0, 0 with a dot. The point, the origin. Yeah, but in the other square, in the big one, nope, to the right, to the right. Yeah, there you go. 0. And where is 1, 0?
1, 0.
Yeah.
1 0 is up here.
No, in the same big square. I mean, the ordered pair 1, 0 in the plane. Yeah. And let's draw a little arrow between those. All the way to 1, 0. Yeah, so you can think of this function as 0, 0 and 1, 0 stay where they're at. The function will map 0 to 0, 0 and So it kind of, the function kind of begins at the origin and ends at 1, 0. And it does the circuitous movement by, it goes up and then down. But the net result is that it begins at 0, 0 and it ends at 1, 0. The next square, when you want to go from the, maybe I can share. Hang on for a second. This will take me a minute.
Wait, no, I see people have wrong square. Is there wrong square? Wait, this is that square. I think it's that there is zero, 1, 0.
Oh, I mirrored the wrong thing here. Are you seeing anything?
Yeah, we see a square.
Okay. So here is the ordered pair 0, 0. And here is the ordered pair 1, 0. And we divide the square into these parts. And we go 0, 1, 2 to 3 to begin. And so we sort of begin here and end here. At the 0 stage, let's do the next stage. We go 0, 1, 2, 3. So that means we've started here, and this time we end up here at this vertex. And this ending vertex becomes the beginning vertex for the next one. And now we end at this one. It becomes the beginning vertex for the next one. Now here's the ending vertex. This becomes the beginning one for the next counting. And we end up at 1, 0 again. Does this make sense? This counting makes sense? And so you can think of these things as I'm going to draw the same kind of picture here. So you can think of what's going on is we'll divide this into 4 equal pieces in this case, and then we will go from there to there, there to there, there to there. This is called the arrow diagram, and it goes from 0 to 1 to 2 to 3. And then at the next stage, each of these 4, I'll try to use another color. So the first arrow diagram is like this. The second arrow diagram is like this. The third arrow diagram is the same as the second, and the last one goes like this. Now, in that paper that I showed you, we called this left, down, down, and right. So these arrow diagrams go left, down, down, right. And the arrow diagram actually determines the order 0, 0, 0, 1, 0, 2, 0, 3. 1, 0, 1, 1, 1, 2, 1, 3. Are we good here? So let's find 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. So let's try a shape again, if I can do this. We better go to black again. So it's in this 0th one right here. And then it's always 1. So we divide that into 4. And this time 0, 1, 2, 3. So that means it's in this one right here, down here. So we need to know how to diagram this. So here was the 0th. And we want to begin here and end here. So this will go like this. And then we want to begin here and end here. And so this will be this shape. So in this one right here, we had the shape that goes to the left. That's our shape, which means 0, 1, 2, 3. You with me? So it's in this lower one right here. And now here's the interesting part, or a part. The one before this also had this shape. 0, 1, 2, 3. So the number 1 square here was to the lower right, and this has the same diagram as we started with. So the next one will be the same. This will be also this. And the number 1 square for that will be this lower piece right here. And that continues. So the point you're interested in is this guy right here. Point 0, 1, 1, 1, etc. So that point is in the Cartesian coordinates is 1/2, 0. We okay with this? It's a little tricky, but there's some information in the base 4 decimal. There's information about the geometry, and you guys were getting it in a fine way. But what you want to look for is a recurring pattern so that you can figure out exactly where that point is. So for homework, I'd like you to figure out a couple of these. One of them is what if you look at the origin, what is f of that? And then f of 0.111 repeating in ones, what is that? F of 0.222, etc. What is that? And f of 0.333. What are these? You know what I mean here? And this one is not hard to figure out. It's the origin 0, 0. But what is this? What is this? What is this? And then you might look at the next stage a little bit. You did 0, 1, 1, 1, but what would it be if you take 0.3, 2, 2, 2? What is this? Or f of 0.2, 0, 0, 0. What is this? And the decimals on the left that I'm using are all base 4 decimals. And these are just regular ordered pairs. I'm going to unshare if that's okay. Because you guys are real little now, I can hardly see you.
Did we put like the TV that they were running through? I think there's a camera and a microphone. That we can. Okay.
So this is to get you kind of used to the things that we talked about today. We talked about a lot, but these things are, the first ones have to do definitely with the problem that we're dealing with. And how to, what to look for and how to create sets of positive measure out of what we're doing. What we just did right now is to give you an idea of how this coding goes for these space filling functions. Here we're using base 4 arithmetic in the domain, which is just like regular decimal arithmetic. And then using that together with the geometry of these squares and how they're ordered in order to figure out the function at various points. Where does this function map things? So I'd like you to be familiar with that and to work out some of these examples for yourself. And then we'll talk about, next time I'd like to talk about notation and how this stuff is denoted. And I'd also like to then, depending on how far you get with a set of positive measure, I'd like you to talk about how we actually code all that stuff in. And you'll want to be familiar with how this stuff works. I think you'll get the idea of it reasonably quickly. And then the question is, how can you compute this stuff pretty quickly? How does it work? How can you control it and be in charge of it and that sort of thing? And during the week, if you can, I'd really like the group to work together on some of this. I think it's really helpful if you work together. And for the usual meetings in this room, I would like you to, I'll ask you to show me what you've got. And you can send me, you can LaTeX up if you want the material that you have, but you can also wait and show me what you have first or ask questions or whatever. And we'll go from there. It sound good? Did it sound like we can do this? Luke sounded pretty sick today. I hope he's not got something bad. But try to maybe you've got each other's email addresses and so on. So please keep Luke in the mix, if you will. I've had Abby and Luke in class, and I've worked with Emma some, and I've worked with Isabel's dad. So I mean, what can you say? So I think a lot of all of you. I think it'll be good to work together. I think you'll be a good team. This will be a really good team, I think. So. And I don't know if I put down my the hotline. Abby, could you write this on the board right now so that everybody has it?
Yeah.
507 301 8475. So anytime you want to talk, you can message me, but give me a call. Let me know what the problem is, or to call you back, and we'll deal with it as soon as I can. I don't necessarily answer immediately, but I can. I mean, be prepared. And please feel free to do that.
Okay.
So we've got this room until at least a little after 4 every Tuesday. And if you would want to use it a different day of the week for the group getting together, let Ellen know. Let me know too, but you can go directly to Ellen. She'll help you out, let you know.
We can always meet in the library.
Have you looked at the videos that are up there on the links that I sent you?
It's just the one video, right? Yeah.
And on we have a shared drive and on that shared drive is this paper from the Math Monthly, and a lot of this is explained in there. But when you're reading math, it can be long and hard, but with what we've done today, you'll be able to see some of this. Are we good for today?
Bless you.
Are we good?
Yeah. Yeah.
Okay. Well, I'll see you next Tuesday, if not before.
Sounds good.
Have a great week, but not too great.
You too.
Yep. Now I'll see you Tuesday.
Thank you.
Oh, thank you.
Bye.
See you soon.